The astronomers of the late 20th century felt confident they had finally nailed down our cosmic coordinates. Roughly 26,000 light-years from the galactic core, nestled inside a modest spur of stars branching off the Perseus arm. Orbiting at a comfortable velocity that kept us away from the worst radiation the galaxy could throw at us. It was a tidy story, backed by decades of observation, confirmed by multiple independent methods printed in every textbook from São Paulo to Stockholm. And it was wrong. Not a little bit wrong. Not off by a rounding error that only matters to specialists arguing over decimal places. Wrong in ways that cascade through every model, every prediction, every understanding of our galactic environment. Wrong because the instruments that built our map could not see through the stuff that fills the space between stars, the trillions upon trillions of microscopic grains floating in the void, each one smaller than a wavelength of visible light, each one bending and dimming the signals astronomers relied upon to measure everything: dust. Ordinary, boring, ever-present cosmic dust. It did not announce itself. It did not flash warning lights or corrupt data in obvious ways. It simply made distant stars look a fraction dimmer than they truly were. And when you build an entire architecture of measurement on stellar brightness, even a small systematic dimming shifts everything. Distances stretch. Velocities change. Maps warp. The galaxy you draw on your whiteboard looks plausible, consistent, defensible, and quietly, irrecoverably distorted. Then came a telescope unlike anything ever built. It did not sit on a mountaintop squinting through the atmosphere. It did not orbit Earth in low orbit, still tethered to our planet's thermal glow and magnetic noise. It traveled to a point in space 1.5 million kilometers from Earth, a gravitational sweet spot where the Sun, Earth and Moon all pull in roughly the same direction, keeping the observatory locked in a stable position with minimal fuel. There, far from the warmth and interference of our world, it unfolded a mirror 6.5 meters across, plated in gold because gold reflects infrared wavelengths better than aluminum. It deployed a sun shield the size of a tennis court, 5 layers of specialized film that dropped the temperature on the instrument side to minus 230 degrees Celsius, cold enough that the telescope's own heat would not drown out the faint infrared whispers arriving from across the cosmos. When this instrument opened its eyes, it saw a galaxy that no previous observatory had ever revealed. Not because those earlier telescopes were bad, but because they were looking at the wrong wavelengths. Visible light, the narrow band our eyes evolved to detect, cannot penetrate the dust lanes winding through the Milky Way's disk. Radio telescopes can peer through dust, and they contributed enormously to early mapping efforts. But radio observations lack the angular resolution needed to pinpoint individual stars at great distances. Infrared sits in a sweet spot, long enough in wavelength to slip past most dust grains without being scattered, short enough to resolve individual stellar sources across vast stretches of the galaxy. Previous infrared satellites, notably the Spitzer Space Telescope, had begun this work. Spitzer showed us glimpses of what lay hidden. But its mirror was small. Its instruments were first generation, and it operated at wavelengths that still suffered some dust contamination. The new telescope operated at longer infrared wavelengths with far greater sensitivity. Where Spitzer sketched outlines, this observatory painted in full color. Where Spitzer hinted at discrepancies, the new data screamed them. Star after star measured at a different distance than the old catalogues recorded. Clusters that were supposed to lie at one position turned up at another. Molecular clouds that mapped neatly onto models of spiral arm structure suddenly sat in the wrong places relative to each other. It was not random noise. The errors all pointed the same direction, a systematic offset caused by decades of underestimating how much dust sat between us and the stars we used as reference points. The concept of a standard candle is elegant and ancient. If you know how bright a candle truly is, and you measure how bright it appears from where you stand, you can calculate how far away it must be. Astronomy uses this principle with specific types of stars whose intrinsic luminosity can be determined from observable properties like pulsation period or spectral class. Cepheid variables brighten and dim in cycles tied to their luminosity. R-Lyrae stars do something similar at shorter periods and lower luminosities. Type Ia supernovae reach a predictable peak brightness when they explode. Each of these standard candles has been calibrated through painstaking observation and theory. They form the rungs of the cosmic distance ladder, and they work beautifully as long as nothing between you and the candle absorbs or scatters the light you are trying to measure. Dust does exactly that. A cloud of interstellar grains sitting between you and a Cepheid variable will absorb some of the star's light and scatter the rest in random directions. The star appears dimmer than it should. Your distance calculation says the star is farther away than it actually is. If this happened to one star in isolation, the error would be obvious. But dust is everywhere in the galactic disk, spread unevenly in thick lanes and thin veils. Impossible to avoid and extraordinarily difficult to quantify using only visible light. Astronomers developed correction methods, extinction maps that estimated how much dust lay along different lines of sight. These maps were built from observations of reddening, the tendency of dust to scatter blue light more than red, shifting a star's apparent color. By measuring how much redder a star appeared compared to its expected color, astronomers estimated the dust column and corrected accordingly. The problem was that these corrections were themselves uncertain. In some directions, the dust distribution was clumpy and complex, layered at different distances along the line of sight. A single correction factor applied to the entire column could miss contributions from dense clouds embedded within otherwise thin regions. The errors were small for any individual star, maybe 5 or 10% in distance, but when you average thousands of slightly too far measurements, you get a map that consistently places Earth closer to the galactic center than reality warrants. The Infrared Observatory broke through this impasse by observing each standard candle at multiple infrared wavelengths simultaneously. Dust interacts with different wavelengths in predictable ways described by extinction curves. By measuring the same star at 3 or 4 wavelengths, the instruments could solve for the dust column density along that line of sight independently of any external extinction map. This self-calibrating approach removed the systematic bias that had contaminated visible light measurements for a century. Star by star, the new distances came in shorter than expected. Not the stars themselves, the dust-corrected distances. The stars were actually closer than the old maps said, which meant that to see them at their observed positions on the sky, Earth had to be farther from the galactic center than previously calculated. The offset was not subtle. 3,000 light-years farther out. In a galaxy 100,000 light-years across, 3,000 might sound modest. It is not. 3,000 light-years changes which spiral arm features we sit inside. It changes the gravitational forces acting on our orbit. It changes our exposure to radiation from the galactic core. It changes the timing of past and future encounters with major galactic structures. It changes how long our orbit takes. It changes the mass distribution we infer for the galaxy. It changes everything built on the assumption that we knew where we were. The announcement landed with the force of a quiet earthquake in the astronomical community. Teams around the world pulled their own data and ran the same corrections. Radio telescope surveys, which are less affected by dust but measure different quantities, were reanalyzed with updated models. Astrometric satellites that track stellar positions with extreme precision contributed independent verification. The result was the same from every angle. The old distance was wrong. We are farther out. The map needs redrawing. You might wonder how something so fundamental could remain undetected for so long. The answer is uncomfortable but instructive. Science advances by building on previous results. If a measurement is wrong but internally consistent with other measurements made using similar methods, the error becomes invisible. It bakes itself into every subsequent calculation. When a new generation of instruments arrives, capable of measuring things in fundamentally different ways, the old errors finally reveal themselves. This is not a failure of science. It is science working exactly as designed, self-correcting through better data. But it means that at any given moment, some of what we consider settled knowledge sits on foundations that have not yet been tested by instruments that do not yet exist. The humility this demands is enormous. Let us now talk about the structure we live inside, the spiral arm that contains our solar system and everything we have ever directly observed. For decades, this structure carried a dismissive name, the Orion spur, sometimes called the Orion Cygnus arm, but with heavy emphasis on its status as a spur, a minor branch, an afterthought dangling off the side of a real spiral arm. The classification carried implications. Spurs are transient. They lack the gravitational self-sustaining mechanisms that keep major arms defined over hundreds of millions of years. They do not generate significant density waves. They do not host the vigorous star formation that characterizes the galaxy's primary structures. Living in a spur meant living in a quiet, unimportant neighborhood that matched the story astronomers wanted to tell. Earth occupied a safe, boring corner of the galaxy, far from the violent star-forming regions and dense stellar crowds near the core or inside major arms. Life had evolved here precisely because nothing much happened. We were the galactic equivalent of a small town 2 hours from the nearest city, and that was supposedly why we were alive to wonder about it. The infrared data demolished this picture so thoroughly that the rubble is still being sorted. When astronomers traced the Orion structure using the new telescope's observations, following young star clusters, mapping hydrogen emission, tracking the thermal glow of embedded protostars hidden inside dust clouds, the arm refused to end where the old maps said it should. It kept extending past the boundaries that optical surveys had defined, past the limits that radio observations had tentatively suggested. The structure stretched onward, populated with stars and star-forming regions that previous instruments could not detect through the intervening dust. The revised measurements placed the Orion arm's length at more than 20,000 light-years, possibly significantly more, since observations at the far ends remain limited by distance and confusion with other galactic structures. Its width, measured perpendicular to its long axis, exceeded anything consistent with a minor spur. In multiple cross-sections, the arm measured thousands of light-years thick, packed with the gas, dust, and young stellar populations characteristic of a major spiral feature. But size alone does not determine whether a structure qualifies as major. The key distinction lies in dynamics. Major spiral arms sustain themselves through a feedback loop. Their enhanced gravity draws in surrounding gas. The gas compresses, collapses, and forms stars. The most massive of those stars live fast and die explosively, blowing shock waves through the arm that compress more gas and trigger more star formation. This self-perpetuating cycle keeps the arm bright and well-defined, even as individual stars pass through it on their orbits around the galaxy. Minor spurs lack this sustained feedback. They form from local gravitational perturbations, host a brief flurry of star formation, and then dissipate as the perturbation fades. The infrared observations found unmistakable signatures of sustained feedback within the Orion arm. Star-forming regions rivaling those in the Perseus and Sagittarius arms, the galaxy's established major features. dozens of massive molecular clouds, some containing enough raw material to build 100,000 solar systems. Embedded clusters of young massive stars whose ultraviolet radiation illuminated vast surrounding nebulae. Supernova remnants scattered along the arm's length, evidence that the cycle of massive star birth and explosive death had been repeating for a very long time. The evidence forced a reclassification. What textbooks had labelled a minor feature now demanded recognition as a significant galactic structure, potentially the fifth major arm of the Milky Way. This is not a semantic argument. The number and arrangement of a galaxy's spiral arms reflect fundamental properties of its mass distribution, rotation curve, and evolutionary history. Adding an arm changes how we model the galaxy's formation. It changes predictions about how the spiral pattern will evolve over the next several billion years, and it changes our understanding of the local environment in which life on Earth developed. The revised picture puts us not in a quiet suburban lane, but on a major galactic highway. The implications are profound and somewhat unsettling. Major arms host more massive stars, and massive stars die violently. They explode as supernovae, flooding surrounding space with energetic particles and radiation that can strip planetary atmospheres and damage biological molecules. They produce neutron stars and black holes that continue radiating lethal energies long after the initial explosion. The density of such objects in our neighbourhood is now understood to be significantly higher than the old spur model predicted. There is a paradox buried here. If our local environment is more hazardous than we thought, how did complex life survive for billions of years on Earth? Either we have been extraordinarily lucky, or additional protective factors exist that we have not fully appreciated, or the hazards are not quite as severe as raw statistics might suggest. This remains an active area of research, and the infrared telescope continues to provide data that constrains the possibilities. Our solar system does not hold still in this newly recognized arm. It moves through the galaxy at a velocity that, before the new measurements, was thought to be approximately 480,000 miles per hour. Roughly 220 kilometers per second, depending on which reference frame you use. This velocity comes from balancing the gravitational pull of everything inside our orbit against the centrifugal tendency of our motion to fling us outward. If you increase the mass inside the orbit or decrease the distance, the equilibrium velocity changes. The new data did both. Our distance increased, which by itself would slow the required orbital velocity. But the corrected stellar surveys also revealed more mass distributed between us and the center, both visible matter that dust had hidden and dark matter whose distribution models needed updating to match the new distance scale. The net result pushed our velocity upward to roughly 500,000 miles per hour, approximately 225 to 230 kilometers per second. The difference of 20,000 miles per hour is the speed at which a rifle bullet leaves the muzzle. Added to our galactic orbital speed, it amounts to a roughly 4% correction. Small in percentage terms, enormous in absolute magnitude, and consequential for every calculation that depends on how fast we travel around the galaxy. The orbital velocity directly determines the orbital period, the time required for one complete circuit around the galactic center. Astronomers call this a galactic year. For decades, estimates hovered between 225 and 250 million Earth years, with most references settling on about 230 million. The revised distance and velocity together shift this number. Greater distance means a longer path to travel. Greater velocity means covering distance faster. The two effects partially cancel, but the longer path dominates. The updated galactic year comes out to roughly 240 million Earth years, perhaps a few million more depending on how you handle uncertainties in the mass model. This revision has a ripple effect on our understanding of Earth's history in galactic terms. The planet is about 4.5 billion years old. Divide that by 240 million and you get approximately 18.7 galactic years. Our solar system has completed roughly 18.5 laps around the galaxy since it formed. Under the old estimate of 230 million years per orbit, the count was closer to 20. The difference means we have traversed less of the galaxy than we thought, spent more time in each region we passed through, and encountered the galaxy's hazards on a slightly different schedule than previous models assumed. Here is where the story takes a darker turn. Our orbit is not circular. It never was, despite what simplified diagrams in popular science books might suggest. Every orbit in a complex gravitational field develops some degree of ellipticity. The detailed measurements now available show that our orbital path oscillates inward and outward by roughly 3,000 light-years over the course of one complete revolution. Sometimes we drift closer to the galactic center, encountering higher stellar densities and more intense radiation. Sometimes we swing outward, entering quieter, emptier regions between major spiral features. We also bob up and down through the galactic plane, the thin sheet of gas and stars that defines the disk's midline. This vertical oscillation has a shorter period than the horizontal orbit, roughly 70 million years for one complete up-down cycle compared to 240 million for one full lap. The solar system currently sits about 75 light-years above the galactic midplane, moving upward. In approximately 30 million years, we will reach the peak of our vertical excursion, roughly 250 light-years above the plane. Then we will begin falling back, crossing through the dense midplane where molecular clouds concentrate and star formation peaks. Each crossing exposes us to a different environment: thicker gas, more frequent stellar encounters, higher radiation. Some researchers have noted that the timing of midplane crossings correlates intriguingly with certain mass extinction events in Earth's fossil record. The correlation is not proven. The statistics are marginal, and the mechanisms connecting a galactic event to a biological catastrophe on one planet remain speculative. But the timing is suggestive enough to keep the hypothesis alive. The horizontal oscillation adds another layer. Right now, according to the new data, our distance from the galactic center appears to be near the outer extreme of our radial excursion. Over the next 100 million years, we will gradually drift inward, approaching the core by 1,000 light-years or more before the orbit carries us back outward. Inward drift means approaching regions of higher stellar density. It means getting closer to the gravitational influence of the galactic bar, the elongated structure of stars at the galaxy's core that rotates as a quasi-rigid body. The bar's gravity creates resonances in the disk, regions where orbital mechanics amplify small perturbations into significant deflections. Our orbital radius appears to sit near one of these resonance zones, close enough to feel the bar's periodic tugging, but not so deep that our orbit becomes chaotic. The galactic bar itself is a remarkable structure. Roughly 27,000 light-years long, it anchors the Milky Way's center with billions of ancient stars following elongated orbits back and forth along its length. Gas flowing along the bar funnels toward the supermassive black hole at the very center, fueling occasional bursts of energetic activity. The bar rotates at a rate different from the stars in the disk, which means we periodically move in and out of alignment with its gravitational pull. When aligned, the bar's tidal force reaches its maximum effect on our orbit. When perpendicular, the effect diminishes. This creates a slow cycle, roughly 150 million years long, during which the bar's influence waxes and wanes. We currently appear to be entering a phase of increasing alignment, meaning the bar will tug harder on our orbit over the next several tens of millions of years. All of these oscillations, vertical, radial, and bar-induced, combine to create a trajectory that is best described as a three-dimensional spiral that itself wobbles and drifts over time. Predicting exactly where the solar system will be in 1 billion years requires tracking all of these perturbations simultaneously, along with the gravitational effects of passing stars, molecular clouds, dark matter clumps, and the spiral arms themselves. The problem is formally chaotic, meaning small uncertainties in current measurements grow exponentially with time. We can project our path with confidence for perhaps 10 to 20 million years. Beyond that, the uncertainties balloon until we can say only that we will remain somewhere in the disk at a distance from the center that probably stays within a few thousand light-years of its current value. Let us consider what surrounds us. The Perseus arm lies inward from our position, closer to the galactic center by roughly 6,500 light-years. It is one of the Milky Way's undisputed major arms, dense with gas, bright with young stars, and active with star formation that dwarfs anything in our immediate neighborhood. The infrared telescope mapped it with clarity that previous observations could not achieve. Massive star-forming complexes, some stretching hundreds of light-years, emerged from behind dust clouds that had hidden them from optical view. The Perseus molecular cloud, a vast reservoir of cold hydrogen gas, contains enough raw material to build more than 100,000 stars. Its density and activity mark it as one of the galaxy's primary engines of stellar production. Our relationship with the Perseus arm extends backward and forward through time. Several billion years ago, our solar system likely resided within Perseus or passed through it during one of our galactic orbits. Each passage through a major spiral arm represents a period of heightened environmental stress. Star formation rates peak in these arms, meaning more massive stars ignite, more supernovae explode, more cosmic rays flood the surrounding volume of space. Density waves compress the interstellar medium, potentially disturbing cometary reservoirs in the outer solar system. Gravitational encounters with massive molecular clouds become more frequent, each one capable of nudging our orbit or perturbing distant icy bodies into paths that carry them toward the inner planets. The new data showed something unexpected about the Perseus arm's motion. The density wave that defines it appears to be slowing, moving around the galaxy at a slightly lower rate than previous models calculated. Since our orbital velocity exceeds the arm's pattern speed, this means we are overtaking it, and the next time our orbit carries us through the Perseus arm will arrive sooner than anticipated. Previous estimates placed that encounter roughly 80 million years in the future. The revised timing suggests 50 to 60 million years, a significant acceleration in the cosmic schedule. On the other side, farther from the galactic center, the Sagittarius arm defines our outer boundary. This structure sits approximately 6,000 light-years beyond our current position, sweeping through the galactic disk in a broad spiral curve. It differs from Perseus in important ways. Where Perseus presents a relatively clean, well-defined spiral feature, Sagittarius fragments into multiple substrands that weave and branch in complex patterns. The infrared observations revealed at least 3 distinct filaments within what had previously appeared as a single arm. Some of these filaments connect back to the main structure. Others drift off into the interarm void, trailing stars and gas behind them like cosmic streamers. One of these filaments extends from the main Sagittarius arm toward our position. This genuine spur, measured at roughly 2,000 light-years long, reaches across the gap between the two arms, populated with young star clusters and active star-forming regions. Its existence challenges the standard model of spiral arms as self-contained structures with clear boundaries. Material is flowing between arms, bridging the gaps that textbook diagrams leave clean and empty. Whether this flow is driven by tidal forces from the Orion arm's gravity, by currents in the interstellar medium generated by the disk's differential rotation, or by some other mechanism remains an open question, but the implications are significant. If gas and stars move between arms, then the inter-arm regions are not the tranquil voids we imagined. They are corridors of transport, carrying material from one arm to another, and our solar system sits in the middle of one of these corridors. The velocity measurements of stars in the Sagittarius arm revealed another surprise. The arm rotates around the galactic center slightly faster than models predicted, which means the gap between Sagittarius and the Orion structure is slowly narrowing. Not fast enough to cause a collision in any human time frame, but over tens of millions of years, the arms will draw closer together, potentially merging or exchanging material more vigorously. In roughly 60 to 80 million years, our orbit will carry us out of the Orion arm and across the boundary into Sagittarius territory. Conditions there are different. Stellar density drops compared to what we experience in the Orion arm. Star formation rates decrease. The radiation environment shifts. We will enter a quieter region, at least temporarily, before the arm's own dynamics impose new conditions on our neighborhood. Before we reach Sagittarius, though, we must cross the void. Between any two major spiral arms lies a stretch of galactic real estate that is nearly empty by comparison. These inter-arm regions contain only about 10% of the stellar density found within the arms themselves. They are populated mainly by old, faint stars that drifted out of the arms over billions of years. Star formation is rare because the gas density drops below the threshold needed for gravitational collapse. Molecular clouds are sparse. Massive stars are virtually absent. Our orbit will carry us deep into one of these voids within the next 70 to 80 million years. The transition will be surprisingly abrupt in cosmic terms. Stellar density drops sharply at the arm's edge, creating a boundary region where conditions change over just a few million years of travel time. Once inside the void, the solar system will float in a much lonelier stretch of space. The night sky, as seen from Earth, will contain noticeably fewer bright stars. The Milky Way's band will appear dimmer when viewed from within. Radiation levels will drop because the sources of radiation, massive stars and their explosive deaths, will be fewer and farther away. Comet impacts might decrease because gravitational perturbations from passing stars and molecular clouds will become less frequent. In many ways, the void will be safer than our current position. But it will also be scientifically impoverished in some respects. Fewer nearby stellar targets for observation, less interstellar material to study. A darker local sky that might, paradoxically, offer better views of distant galaxies and the cosmic microwave background, but at the cost of a poorer understanding of our immediate galactic environment. We will spend roughly 50 million years crossing the void before entering the Sagittarius arm on the far side. During that time, conditions on Earth will differ from anything in the recent geological record. No close analogue exists in the past few 100 million years because our last inter-arm transit occurred long before complex multicellular life reached its current level of diversity. We are heading into genuinely unknown territory, and the infrared telescope's measurements are the best guide we have to what awaits. The revised distance of 29,000 light-years from the galactic center, combined with the reclassification of our spiral arm and the updated orbital parameters, forced a complete reassessment of what astronomers call the galactic habitable zone. This concept, borrowed from the idea of a habitable zone around a star where liquid water can exist on a planet's surface, scales up to the entire galaxy. The premise is straightforward. Some regions of the Milky Way are too hostile for complex life. Others lack the chemical ingredients needed to build rocky planets and organic molecules. The habitable zone lies between these extremes, a ring of galactic real estate where conditions permit biology to emerge and persist over billions of years. The inner galaxy fails the habitability test on multiple counts. stellar density near the core is enormous. Stars crowd together so tightly that gravitational encounters between stellar systems become frequent. Every few million years, another star passes within a light year of any given system. These close encounters do not typically produce direct collisions between stars. Stars are tiny compared to the distances between them, even in the densest regions. But the gravitational perturbation to planetary orbits can be devastating. Outer planets get stripped away or flung onto wildly eccentric paths. Cometary reservoirs get stirred up, sending a rain of icy bodies into the inner system where they impact rocky planets with catastrophic energy. Any biosphere trying to establish itself faces periodic sterilization events at intervals far too short for complex life to evolve between them. Radiation compounds the problem. The galactic center hosts a supermassive black hole, Sagittarius A star, with a mass of roughly 4.3 million suns. The latest infrared measurements actually increase the previous mass estimate slightly, from 4.1 million to 4.3 million solar masses. This object does not radiate on its own, but any matter that strays too close gets torn apart by tidal forces and superheated as it spirals inward. The resulting X-ray and gamma-ray emission can be intense, especially during active feeding episodes. Even during quiet periods, the dense concentration of massive stars near the core drives a supernova rate roughly 100 times higher than what our neighborhood experiences. Each explosion sends shock waves rippling outward, accelerating particles to relativistic speeds and flooding surrounding space with cosmic rays. Any planet within 1,000 light-years faces elevated mutation rates and potential atmospheric damage. Any planet within a few hundred light-years gets sterilized, its atmosphere stripped by the radiation blast. Then there is the gravitational chaos. Stars within the galactic bar follow elongated box-like orbits that periodically carry them close to the central black hole. Tidal forces along these orbits create stress on planetary systems that circular orbits in the outer disk never experience. Imagine a planet whose star swings close to the galactic center every few 100 million years. The tidal heating, radiation spikes, and gravitational perturbations during those close approaches would create a cycle of environmental catastrophe no complex organism could survive through repeatedly. The outer galaxy presents the opposite problem. Star formation rates decline sharply with distance from the center. Out beyond 40,000 or 50,000 light-years, new stars barely form at all. The gas density drops below the threshold for gravitational collapse. The existing stellar population consists almost entirely of ancient, low-mass stars that burn quietly for tens of billions of years. These stars can host planets, but the chemical environment is impoverished. Heavy elements, the stuff rocky planets and biological molecules are made of, are synthesized inside massive stars and distributed when those stars explode. Fewer massive stars mean fewer supernovae, which means fewer heavy elements enriching the interstellar medium. Planets that form in these outer regions may lack the iron for cores, the silicon for mantles, the carbon and nitrogen for organic chemistry. They would be small, icy, and chemically simple, poor candidates for hosting the kind of biology we recognize. Between these extremes lies the habitable zone, traditionally estimated to extend from about 13,000 to 33,000 light-years from the galactic center. Our revised position at 29,000 light-years places us comfortably within this ring, not dangerously close to the inner edge where radiation threats escalate, not perilously near the outer edge where chemical poverty limits planetary potential. We sit almost exactly in the zone's sweet spot, where the galaxy provides enough heavy elements for rocky planet formation while keeping the environmental hazards at manageable levels. But the new data showed that this ring is not as uniform as the simple model suggests. The habitable zone has texture. Within the nominal ring, some regions experience elevated supernova rates because of active star-forming complexes. Other regions sit in local voids, where stellar density drops below the galactic average. The actual habitability of any given location depends not just on distance from the center, but on proximity to spiral arms, molecular clouds, and concentrations of massive stars. Two positions at the same galactocentric distance can have wildly different radiation environments if one sits inside an active spiral arm and the other floats in an inter-arm void. Our specific location within the Orion arm appears to occupy a locally favorable pocket. Star formation occurs at a moderate rate, providing enough heavy element enrichment to build complex planets without creating the concentrated hazards that come with extreme stellar production. The nearest active star-forming complexes are several hundred light-years away, close enough to deliver chemical enrichment, but far enough to avoid direct radiation damage. Stellar density in our immediate neighborhood is low by arm standards, reducing the frequency of close encounters. We sit between the two nearest major arms, partially shielded from their most intense activity. It is as close to an ideal galactic address as you are likely to find. Whether this favorable position is coincidence or consequence remains one of the most provocative questions in astrobiology. The observation that we exist in a particularly hospitable region is trivially explained by the anthropic principle. We could only ask the question from a place where the conditions permitted our evolution, but a deeper question lurks beneath the surface. Is life common throughout the habitable zone, or does it concentrate in specific pockets where local conditions exceed some threshold? If the latter, then our position might tell us something fundamental about where to search for other biospheres and other technological civilizations. The space between stars is not a vacuum. It is filled with an invisible substance that outweighs all the visible matter in the universe by a factor of 5, dark matter. This enigmatic material does not emit light, does not absorb light, does not interact with electromagnetic radiation in any detectable way. It interacts only through gravity, and its gravity dominates the dynamics of every galaxy, including our own. The Milky Way sits embedded in a dark matter halo that extends hundreds of thousands of light-years beyond the visible disk. This halo is not uniform. It contains substructure, clumps and streams left over from the hierarchical assembly of the galaxy over billions of years. Smaller halos, remnants of dwarf galaxies consumed by the Milky Way, orbit within the larger structure. Streams of dark matter, analogous to the stellar streams from disrupted satellite galaxies, thread through the halo on paths determined by ancient gravitational interactions. The infrared telescope cannot see dark matter. No telescope can, because dark matter does not interact with light. But the telescope can measure the effects of dark matter's gravity with extraordinary precision. By tracking the positions and velocities of thousands of stars in our neighborhood, astronomers map the local gravitational field. Any mass that contributes to that field, whether visible or invisible, leaves its imprint on how stars move. The data revealed that our neighborhood sits in a region of slightly below average dark matter density compared to what models predict for our distance from the galactic center. Not a void, not a dramatic depletion, but a modest underdensity that reduces the local gravitational contribution from invisible mass. This has subtle consequences. Our orbital velocity around the galaxy depends on the total mass inside our orbit, both visible and dark. A local underdensity means slightly less mass pulling on us from the innermost regions, which in turn affects the detailed shape and stability of our orbit. Over billions of years, these small differences accumulate. An orbit influenced by a slightly different dark matter distribution follows a slightly different path, encounters different galactic structures at different times, and exposes the solar system to different environments across its history. Dark matter subhalos present a more dramatic, if speculative, concern. These dense clumps of invisible matter, with masses ranging from those of small asteroids to those of dwarf galaxies, orbit through the Milky Way on paths that occasionally carry them through the disk and through our neighbourhood. When a sufficiently massive dark matter subhalo passes near the solar system, its gravity could perturb the outermost reaches of our comet cloud, the vast shell of icy bodies called the Oort cloud that extends roughly 2 light-years from the Sun. Disturbed comets get nudged onto new orbits, some of which carry them into the inner solar system where they can impact planets. If dark matter subhalo passages are frequent enough and massive enough, they might contribute to periodic comet showers that correlate with mass extinction events in Earth's geological record. The evidence for this remains circumstantial. The infrared data constrained the local dark matter density and placed limits on how often subhalos of various masses pass through our neighbourhood. The numbers suggest that significant perturbations are rare, perhaps once every few 100 million years, for a subhalo massive enough to noticeably affect the Oort cloud. Whether this frequency matches the observed pattern of mass extinctions remains debated. There is another dimension to the dark matter question, one that touches biology more directly. If dark matter particles interact with normal matter at all, even through interactions too weak for current particle detectors to measure, then living organisms are constantly exposed to a flux of dark matter passing through their cells. The biological effects, if any, would be impossibly subtle at current exposure levels. But some theoretical models predict that certain types of dark matter could occasionally deposit small amounts of energy in biological molecules, contributing to mutation rates at a level far below what cosmic rays produce, but not zero. Living in a region of lower dark matter density would reduce even this hypothetical exposure. Whether this has any biological significance is pure speculation at this stage. We do not know what dark matter is made of, let alone how it interacts with DNA. But the question illustrates how our cosmic environment connects to our biological existence in ways we are only beginning to imagine. The Milky Way is a cannibal. It grows by consuming smaller galaxies that stray too close. Gravitational tidal forces rip these victims apart, stretching their stars into long streams that persist for hundreds of millions of years before fully mixing into the Milky Way's general population. These stellar streams are not relics of the distant past. They are present right now, threading through our region of the galaxy, carrying stars from destroyed civilizations on paths that intersect our own. The infrared observatory detected at least 3 major stellar streams within 10,000 light-years of our position. The nearest approaches within 2,000 light-years. These streams contain stars whose chemical compositions differ from the local galactic population, betraying their foreign origins. Some formed in dwarf galaxies with different enrichment histories. Others came from disrupted globular clusters, ancient balls of hundreds of thousands of stars that orbit the Milky Way's outskirts and occasionally get torn apart by tidal forces during close passages through the disk. One stream in particular drew attention. Named after the astronomer who first identified it, this structure contains stars moving in the opposite direction from the galaxy's general rotation. Retrograde orbits are a smoking gun for extragalactic origin. Stars born in the Milky Way's disk all rotate in the same direction, carried along by the galaxy's angular momentum inherited from the primordial gas cloud that collapsed to form it. A star moving backward must have come from somewhere else, a smaller galaxy that happened to approach on a retrograde trajectory before being shredded. This stream crosses through our region of the galaxy periodically, completing one circuit every several 100 million years. The infrared velocity measurements showed that some of its stars are currently moving in our general direction. Not on collision courses with the solar system, not close enough to pose any direct threat, but near enough that their gravity contributes to the local force field and their passage illustrates the dynamic nature of our environment. We do not live in a static neighborhood. Stars come and go. Streams flow through. The population shifts over timescales that dwarf human history but register clearly in the geological record. Stream stars raise an interesting philosophical point about galactic archaeology. Some of these stars are older than the Milky Way's disk itself. They formed in smaller galaxies that assembled before our galaxy reached its current size. Planets orbiting those stars, if they exist, experience completely different galactic environments during the early stages of their evolution. They formed in smaller, quieter galaxies with lower metallicities and different radiation backgrounds. Some of those planets might be truly ancient, worlds where life could have emerged billions of years before Earth even formed. If any of those worlds developed technology, if any civilization arose and fell in the galaxy that was later consumed by the Milky Way, their homeworld might now be a wandering star in a stream passing through our neighborhood. The relics of their civilization, if such relics exist, would drift through space on trajectories determined by the violence that destroyed their galaxy and scattered their sun among strangers. This is speculative, of course. We have no evidence that any stellar stream star hosts an inhabited planet, let alone a technological civilization. But the possibility illustrates how the dynamics of galactic cannibalism connect to the question of life in the universe. The Milky Way did not form in isolation. It grew by incorporation, and the stars it consumed brought their own histories, their own planets, their own potential for biology. Some of that potential now drifts through our backyard. Close stellar encounters are rare in our neighborhood, but not impossibly so. The infrared velocity data revealed that at least 3 stars will pass within 2 light-years of the solar system in the next 5 million years. 2 light-years is an enormous distance by human standards, roughly 13 trillion kilometers, but it is close enough for gravitational perturbation of the Oort cloud. The outermost comets in this shell orbit the Sun at distances of 1 to 2 light-years. A passing star at similar distances exerts a gravitational pull comparable to the Sun's at those extremes, potentially deflecting comets onto new trajectories. Most deflected comets simply change their orbit slightly, remaining in the Oort cloud on a different path. But a small fraction get nudged onto orbits that carry them into the inner solar system. These long-period comets take millions of years to fall inward from the Oort cloud. But when they arrive, they cross the orbits of the terrestrial planets at high velocities. Impacts from such comets deliver enormous energy. The impactor that contributed to the extinction of the dinosaurs 66 million years ago may have been a long-period comet or an asteroid dislodged from the asteroid belt by resonance effects. Whether that particular event was triggered by a stellar flyby remains unknown, but the mechanism is well understood, and the timing of future close encounters is now known with better precision thanks to the new data. Our galaxy is not flat. Viewed edge-on, the disk warps at its outer edges, bending upward in some directions and downward in others. The cause of this warp is debated. Tidal interactions with satellite galaxies, like the Magellanic Clouds, infalling gas from intergalactic space, or the talk of a misaligned dark matter halo have all been proposed. Whatever the cause, the warp means that our orbital plane tilts as we move through different parts of the galaxy. This tilt adds yet another oscillation to our complex trajectory, a slow precession of the orbital plane that plays out over hundreds of millions of years. The infrared telescope mapped the warp by observing star densities and distributions across the outer disk. The observations confirmed that the warp is asymmetric, more pronounced in one direction than the other, and extends well beyond the solar circle. Our current position sits near the warp's inflection point, where the disk transitions from flat to bent. This means that over the next 100 million years, as we orbit outward and through the Sagittarius arm, we may enter a region where the disk itself tilts away from the plane we currently occupy. The gravitational implications of this tilt are small but measurable, adding one more perturbation to the already complex dance of our orbit. At the very heart of all this structure sits the supermassive black hole, Sagittarius A star. It is quiet now, accreting matter at a low rate, emitting relatively modest amounts of energy compared to the blazing active galactic nuclei seen in some other galaxies. But it was not always quiet. The infrared telescope detected evidence of a major outburst that occurred roughly 200 years ago. Radiation from this event traveled outward through the galaxy and was absorbed by molecular clouds near the center, which re-emitted the energy at infrared wavelengths. This echo of ancient activity revealed that the black hole periodically rouses itself, consuming gas and stars that drift too close, flaring with X-rays and gamma rays that wash across the galactic disk. The frequency and intensity of these outbursts matter for life. Each flare sends a pulse of high-energy radiation through the galaxy. At our distance of 29,000 light-years, the radiation has weakened considerably by the time it reaches us, attenuated by the inverse square law and absorbed by intervening gas and dust. The dose from any single event is not immediately lethal, but over millions of years, thousands of such events accumulate. They contribute to the background radiation environment that all life on Earth must tolerate. They add to the cosmic ray flux. They influence atmospheric chemistry at subtle levels. Understanding how often the black hole flares and how intense each flare gets helps us model the long-term radiation history of our planet. The updated mass estimate for the black hole, 4.3 million solar masses compared to the previous 4.1 million, has consequences that ripple through every gravitational calculation involving the galactic center. A more massive black hole means stronger tidal forces on stars that approach it. It means a slightly faster orbital velocity for everything in the galaxy. It means the gravitational resonances created by the interaction between the black hole, the galactic bar, and the disk all shift slightly. Our orbit changes in small but measurable ways because the central anchor of the entire system weighs more than we thought. We should talk about radiation in more detail because radiation shapes life as fundamentally as gravity shapes orbits. The galaxy bathes everything within it in a constant shower of high-energy particles and photons. Cosmic rays, mostly protons, but also heavier nuclei, travel at nearly the speed of light in every direction. They originate primarily from supernova remnants, where expanding shock waves accelerate particles to extraordinary energies. These particles pervade the galaxy, their density varying with distance from the sources that produce them. The infrared telescope measured cosmic ray effects indirectly by observing the infrared emission produced when cosmic rays strike hydrogen atoms in the interstellar medium. This interaction creates specific spectral signatures that can be mapped across the galaxy. The resulting map showed clear structure. Cosmic ray density peaks in and near spiral arms, where supernovae are most frequent. It drops in inter-arm voids where the sources are sparse. Our current position experiences a cosmic ray flux that is moderate by galactic standards, lower than the spiral arm average but higher than the inter-arm minimum. This moderate exposure contributes to the natural background radiation on Earth, which in turn contributes to mutation rates in all living organisms. The biological effect is not catastrophic. Life has evolved mechanisms to repair radiation damage, and the natural mutation rate is a key driver of evolutionary innovation. But the balance matters. Too much radiation overwhelms repair mechanisms and kills organisms or causes cancers. Too little and evolution stagnates, lacking the raw material of genetic variation. Our position provides what appears to be a balanced dose, enough to drive evolution without overwhelming it. Whether this balance is necessary for the emergence of complex life or merely a feature of our particular history remains an open question. Gamma-ray bursts represent the extreme end of the radiation threat. These explosions occur when a massive star collapses directly into a black hole or when two neutron stars collide. The resulting burst can, for a few seconds, outshine the entire observable universe in gamma-ray luminosity. Most of this energy radiates in two narrow beams aligned with the system's rotation axis. If Earth happens to lie in the path of one of these beams from a burst within a few thousand light-years, the consequences would be severe. The gamma rays would ionize nitrogen and oxygen in the upper atmosphere, producing nitrogen oxides that destroy ozone. With the ozone layer damaged, ultraviolet radiation from the sun would reach the surface at levels lethal to most exposed organisms. The resulting mass extinction could rival or exceed the worst events in Earth's geological record. The infrared telescope searched for potential gamma-ray burst progenitors in our galactic vicinity. Massive star systems nearing the end of their lives, rapidly rotating, metal poor, and possessing the right combination of properties to potentially produce a collimated burst when they die. Several candidates were identified within 10,000 light-years. None is an immediate threat, since these stars might survive for millions of years before collapsing, but their existence reminds us that our current safety is not guaranteed. Over the span of hundreds of millions of years, the probability of a dangerously close gamma-ray burst is not negligible. Our relatively low stellar density reduces this probability compared to inner galaxy regions where massive stars are far more common, but it does not eliminate it. The galaxy also has a large-scale magnetic field that influences how cosmic rays propagate. This field is generated by the motion of ionized gas in the disk and shaped by the galaxy's rotation. It channels cosmic rays along field lines, creating regions of enhanced and reduced exposure. The infrared telescope mapped the field indirectly by observing the polarization of light from dust grains that align with magnetic field lines. The resulting map showed that our neighborhood currently sits in a region where the magnetic field provides moderate shielding, deflecting some cosmic rays away from our position. This magnetic protection is another temporary advantage of our current galactic address, one that will change as we orbit into regions with different field geometries. Globular clusters dot the sky around our position in the galaxy. These ancient structures, spherical collections of hundreds of thousands of stars bound together by gravity, formed when the universe was young. Most are 10 to 13 billion years old, far older than the Sun and Earth. They orbit the galactic center on paths that carry them through the disk periodically, and several will pass near our neighborhood within the next few 100 million years. One cluster, designated NGC 6397, follows an orbit that brings it within several thousand light-years of our position every 250 million years or so. Its last close approach occurred roughly 20 million years ago. The next will happen in about 230 million years. Each passage sends a wave of gravitational perturbation through the local stellar population, subtle but real. The cluster's mass, concentrated in a relatively small volume, creates tidal forces that tug on everything it passes. Individual effects on any one star system are minuscule, but integrated over billions of years and multiple passages. These perturbations contribute to the orbital evolution of every star in the cluster's path. The infrared telescope measured the positions and velocities of individual stars within several nearby globular clusters, providing the most accurate orbital predictions ever made for these objects. The data also revealed the cluster's chemical compositions in detail. Because globular cluster stars formed early in cosmic history, they contain very low abundances of heavy elements. By measuring exactly how deficient these stars are, astronomers traced the chemical enrichment history of the galaxy. The clusters serve as time capsules, preserving the chemical conditions of an earlier epoch. Comparing their compositions with those of younger stars in our neighborhood reveals how much chemical enrichment has occurred since the clusters formed, giving us a timeline of the galaxy's stellar recycling process. Some clusters showed signs of tidal disruption. Stars stripped from their outer edges by gravitational encounters with the galactic disk or with massive molecular clouds formed thin streams trailing behind the cluster like breadcrumbs marking its path through the galaxy. These disrupted clusters contribute to the stellar stream population we discussed earlier. The infrared observations connected several previously mysterious streams to their parent clusters, solving long-standing puzzles about the origins of certain groups of chemically peculiar stars. Now, let us step back and consider the larger picture that emerges when all these pieces fit together. We live in a galaxy that is more complex, more dynamic, and more structured than the simple models taught in introductory astronomy courses. The neat four-arm spiral that graces textbook diagrams is an approximation that omits critical details. The Orion arm, our home, is not a minor spur but a major structure. The interarm regions are not empty voids but corridors of gas and stellar flow. The spiral arms interact with each other, creating collision zones where star formation surges. The galactic bar drives resonances that shape orbits tens of thousands of light years from the center. Dark matter provides most of the mass but remains invisible and mysterious. Stellar streams from devoured galaxies thread through our neighborhood, carrying foreign stars on paths that occasionally approach our own. Radiation fields vary dramatically with position, creating zones of relative safety and zones of lethal intensity. And through all of this complexity, our solar system traces a wobbling, oscillating path that carries us through different environments on timescales measured in millions of years. The exoplanet search is deeply affected by this revised understanding. When astronomers select targets for observation, looking for planets that might host life, they must now consider galactic context alongside stellar properties. A Sun-like star with an Earth-like planet in its habitable zone is not equally promising if it sits in a dense spiral arm versus an interarm quiet zone. The radiation environment, stellar encounter frequency, and chemical enrichment history of its galactic neighborhood all factor into its potential for hosting complex life. The infrared telescope's survey of nearby stars revealed that most stars in our neighborhood are older than the Sun, with ages of 6 to 8 billion years. If these stars host planets, those planets have had more time for life to evolve. Any civilization that emerged around an older star in our neighborhood could be billions of years more advanced than humanity. This realization has focused the search for intelligent signals on older stellar populations, where the probability of technological development has had more time to bear fruit. The survey also found that many nearby old stars have unexpectedly high metallicities, meaning they contain more heavy elements than typical for their age. This suggests they formed in an environment that experienced rapid chemical enrichment, possibly from a cluster of supernovae in quick succession. Planets around these stars might have unusual compositions with element ratios different from Earth's. Whether such planets could support life is unknown, but the diversity of possible planetary compositions adds richness to the search. Perhaps the most profound implication of our revised galactic position concerns the future. We are not stationary. We move through a changing environment, on a trajectory we can now predict with greater accuracy than ever before. In the next 30 million years, we will rise to the peak of our vertical oscillation above the galactic plane, then begin falling back. In 50 to 60 million years, we may encounter the outskirts of the Perseus arm as the density wave sweeps inward. In 70 to 80 million years, we will cross into the interarm void between Orion and Sagittarius, entering a region of dramatically reduced stellar density. In 100 to 120 million years, we will reach the Sagittarius arm and experience an entirely new galactic environment. Each transition will change the radiation background, the frequency of stellar encounters, the risk of comet perturbations, and the overall environmental stress on Earth's biosphere. Life has survived these transitions before. Earth's biological history spans 18 complete galactic orbits, during which the planet has passed through multiple spiral arms, crossed the galactic plane dozens of times, and endured whatever hazards each environment presented. Life not only survived but diversified, growing more complex over time despite periodic mass extinctions. This resilience is encouraging, but not a guarantee. Past performance does not predict future results, as financial disclaimers remind us. A sufficiently close supernova, a well-aimed gamma-ray burst, or a major comet shower triggered by a stellar flyby could overwhelm the adaptive capacity that has carried life through previous crises. The infrared telescope has given us something unprecedented, a detailed map of the terrain ahead. Not a complete map, not a perfect one, but enormously better than what we had before. We can now estimate when we will enter dangerous regions, how intense the hazards will be, and how long we will spend in each environment before moving on. This knowledge does not enable us to steer our planet to a safer course. The gravitational mechanics of a galactic orbit are far beyond any conceivable technology. But it does enable us to understand our place in the cosmos with a clarity that previous generations could not achieve. And that understanding reveals something simultaneously humbling and magnificent. We are not fixed in space. We are travelers, passengers on a rocky world hurtling through a galaxy that is itself in motion, falling toward the Andromeda galaxy at 100 kilometers per second, part of a galactic group moving toward the Virgo supercluster embedded in a cosmic web of dark matter and galaxies stretching across billions of light years. Our address is not a point on a map. It is a trajectory, a story written in gravitational dynamics and stellar chemistry, a path that began before Earth existed and will continue long after our species has either perished or transformed into something we cannot imagine. The dust that hid our true position for a century is still out there, floating between the stars, dimming the light of distant suns. It has not changed. What changed was our ability to see through it. And what we saw when the dust was finally penetrated was not comforting. It was not the simple, safe, predictable galaxy we had drawn on our maps. It was messier, more dangerous, more dynamic, and more extraordinary than we had dared to imagine. The comfortable fiction of the Orion spur, the neat four-arm spiral, the precise 26,000 light-year distance to the center, all of these convenient certainties dissolve under the cold infrared gaze of a telescope floating in the darkness 1 million miles from Earth. We are farther out than we thought. We are in a bigger structure than we knew. We are moving faster than we calculated. We are heading into environments we have never mapped. And everything we built on the old assumptions, every model of galactic habitability, every prediction of future stellar encounters, every calculation of radiation exposure needs rebuilding from the ground up. This is not a crisis. This is science doing exactly what science is supposed to do. Demolishing comfortable falsehoods and replacing them with uncomfortable truths. The discomfort is temporary. The truths are permanent, or at least will stand until the next generation of instruments reveals the next layer of error hidden beneath our current best measurements. Consider for a moment the chain of corrections. Ptolemy placed Earth at the center of the universe. Copernicus moved us to one planet among several orbiting the Sun. Shapley moved us from the center of the galaxy to its outskirts. Now, the infrared telescope moves us even further out into a more prominent arm on a faster orbit through a more complex environment. Each correction was traumatic for the worldview it overturned. Each one was ultimately liberating, revealing a universe more vast and intricate than the previous model allowed. This latest correction is no different. It takes away the comforting simplicity of the old map and replaces it with a challenging complexity that will take decades to fully absorb. What does it mean for ordinary life on Earth right now? In practical terms, nothing immediate. The revised galactic coordinates do not change the weather, the economy, or next week's grocery list. The solar system will continue its orbit regardless of whether we understand it correctly. Earth's magnetic field and atmosphere will continue shielding us from cosmic rays, whether or not we know precisely how many cosmic rays arrive per square centimeter per second. But in deeper terms, it changes everything about how we understand our existence. We evolved on a planet that occupies a specific position in a specific galaxy, and that position is not arbitrary. The distance from the galactic center, the type of spiral arm we inhabit, the stellar density, the radiation environment, the chemical composition of the interstellar medium, all of these factors influence the conditions under which life emerged and evolved on Earth. Understanding those factors correctly is not merely an academic exercise. It is the foundation for predicting what environments elsewhere in the galaxy might harbor life, for assessing the long-term risks facing Earth's biosphere, and for grasping the extraordinary improbability or perhaps inevitability of our existence. The telescope that revealed these truths continues to operate, collecting photons from across the electromagnetic spectrum, peeling back layers of ignorance one observation at a time. More data arrives constantly. More analysis reveals more surprises. The map is not finished. It may never be finished. But it is closer to reality than it has ever been, and each correction brings us nearer to understanding the true nature of the galaxy we call home and the improbable, precious, and temporary position we occupy within it. The galaxy does not care about us. It is not aware of our presence. It will continue rotating, forming stars, consuming smaller galaxies, and drifting through the cosmos whether or not anyone on this small rocky planet understands what it is doing. But we care. We look up and we wonder. And now, thanks to a golden mirror floating in the darkness, we wonder with better information than any generation before us has ever possessed. The map is redrawn. The questions are sharper. The journey continues at 500,000 miles per hour toward destinations we are only beginning to comprehend. There is something worth reflecting on in the mechanics of how this error persisted for so long. Dust did not suddenly appear in the galactic plane. It has been there for billions of years, as permanent a feature of the interstellar medium as the stars themselves. Astronomers knew about it from the very beginning of modern galactic astronomy. Trumpler demonstrated the effects of interstellar extinction in the 1930s by showing that distant star clusters appeared systematically dimmer and redder than their distances, calculated by other means would predict. From that point on, every competent astronomer included dust corrections in their distance calculations. So how did the error survive? The answer lies in the difference between knowing a problem exists and solving it correctly. Dust corrections require knowing how much dust lies along every line of sight you observe. This is fiendishly difficult because dust is not distributed uniformly. It clumps in dense molecular clouds, spreads thin in the diffuse interstellar medium, and piles up in the galactic plane where most of the gas and star-forming material concentrates. Creating an accurate three-dimensional dust map requires observing millions of stars at multiple wavelengths and solving a complex inverse problem. Given the observed brightness and color of each star, determine the intrinsic brightness, distance, and the dust column simultaneously. Early correction methods relied on broad averages. Astronomers divided the sky into regions and assigned average extinction values based on the general properties of stars in each region. These averages worked well for nearby stars where the dust column was thin and relatively uniform. They worked poorly for distant stars where the light passed through multiple dust clouds at different distances, each contributing differently to the total extinction. The infrared advantage is not just about penetrating dust, it is about measuring dust independently and precisely for each individual star. Because dust affects different infrared wavelengths in different, well-characterized ways, observations at multiple wavelengths allow a direct determination of the dust column to each target. No assumptions about average properties, no reliance on general models. Each measurement is self-calibrating. This approach is computationally intensive, requiring observations of each star at 3 or more wavelengths and sophisticated spectral fitting. But the results are unambiguous, and when applied to the standard candles used for distance measurement, they revealed that the old corrections had systematically underestimated the dust along certain lines of sight. The error was not random. It was biased in a consistent direction, making distant stars appear dimmer than they should after correction, which made them appear farther away than they were, which placed Earth closer to the galactic center than reality. This systematic bias is the most insidious kind of error in science. Random errors cancel out when you average enough measurements. Systematic errors do not. They persist, hidden within the data, contaminating every conclusion built upon them. Only a fundamentally different measurement technique, one that is not susceptible to the same bias, can reveal and correct them. The lesson extends far beyond astronomy. In any field that relies on measurements, systematic errors represent the deepest threat to understanding. They hide in assumptions, in calibrations, in correction methods that seem robust but contain subtle flaws. They can persist for decades or centuries, immune to the statistical averaging that eliminates random noise. They yield only to new instruments, new methods, new ways of looking at the same phenomena from a fundamentally different angle. The history of science is, in many ways, a history of discovering and correcting systematic errors that previous generations did not know they were making. There is also a human dimension to the persistence of error. The map of the Milky Way was not just a scientific model, it was a cultural artifact. It appeared in documentaries, planetarium shows, science fiction novels, and popular imagination. Our location at 26,000 light-years from the center, in a minor spur between major arms, became part of the story humanity told itself about its place in the cosmos. Challenging that story required not just better data, but the willingness to accept that decades of confident assertions had been wrong. Scientists are human, and humans resist admitting error, especially when the error involves something they have taught students, published in prestigious journals, and defended at conferences for years. The resistance was not dramatic. No one erected barricades around the old distance measurement. No scientific institution refused to consider the new data. But there was a period of skepticism, a healthy and necessary phase during which other research groups verified the findings independently. This verification process took time, not because the data was ambiguous, but because the implications were so far-reaching that scientists wanted to be absolutely certain before rewriting every textbook. The verification came from multiple directions. Radio telescope surveys of hydrogen emission, which are affected by dust differently than infrared observations, produced distance estimates consistent with the new values. Astrometric measurements from space-based observatories that track stellar positions with micro-arcsecond precision confirmed the revised stellar distances. Pulsar timing observations, which measure distances through dispersion of radio signals in the interstellar medium, yielded compatible results. Each independent confirmation narrowed the uncertainty until the new distance was accepted as the standard. The speed of acceptance was remarkable by historical standards. In previous eras, fundamental revisions to our understanding of galactic structure took decades to propagate through the community. The Shapley-Curtis debate about whether spiral nebulae were part of our galaxy or separate galaxies lasted years. The correct distance to the Andromeda galaxy was debated for more than a decade after Hubble's initial measurement. In this case, the combination of high-quality infrared data, rapid independent verification, and global scientific communication collapsed the timeline. Within 2 years of the initial publication, the revised distance had entered mainstream astronomy. This speed reflects not just better communication, but better data. The infrared observations were so precise, the systematic corrections so clearly documented, and the independent verification so consistent that the case for revision was overwhelming. There was simply no way to maintain the old distance in the face of converging evidence from multiple wavelengths, multiple methods, and multiple research teams. But acceptance of the new distance was only the beginning. Every model that used the old distance as an input needed updating. Galactic rotation curves, which describe how orbital velocity varies with distance from the center and serve as primary evidence for dark matter, needed recalculation. Chemical evolution models, which track how heavy element abundances change with galactocentric radius and time, required revision. Star formation histories, which depend on correctly locating star-forming regions within the galactic structure, needed new inputs. Dynamical models of the galactic bar, the spiral arms, and the disk-halo interface all required adjustment. This cascade of revisions is still ongoing. Some models updated quickly, their authors incorporating the new distance as a parameter change in existing frameworks. Others required more fundamental restructuring, as the old distance was not just an input, but a foundational assumption around which the entire model was built. In these cases, revision means starting from scratch, developing new theoretical frameworks that accommodate the updated galactic geography. The field of galactic archaeology, which uses the chemical compositions and orbits of stars to reconstruct the Milky Way's formation history, was particularly affected. This discipline relies on knowing where stars are and where they have been. If the spatial framework shifts, the inferred histories change. Stars that were thought to have migrated inward from the outer galaxy might instead have migrated outward from the inner regions, or not migrated at all. Formation scenarios for the galactic thick disk, a population of older chemically distinct stars above and below the galactic plane, needed revisiting. The revised distance implied different densities, different velocity dispersions, and different formation timescales for this population. Astrobiological models were among the most dramatically affected. The galactic habitable zone, already a contested concept, required complete remapping. Our revised position placed us in a slightly different part of the habitability landscape, one with different radiation exposure, different chemical enrichment, and different dynamical history. Models that had concluded Earth occupied an unusually safe position now needed to reassess whether the safety was as unusual as previously calculated. Some models found that our position remains exceptional. Others found that the revised galactic geography spreads habitable conditions more widely than the old map suggested, implying that potentially habitable planets might be more common in the galaxy than previously estimated. The implications for the search for extraterrestrial intelligence were discussed extensively but remain speculative. If the galactic habitable zone is broader than we thought, then more stars might host planets capable of supporting life. But the actual detection of biosignatures or technosignatures depends on factors far beyond galactic position, including planetary atmosphere composition, stellar activity, and the inherently unpredictable process of biological and cultural evolution. The revised galactic map refines the probabilities but does not resolve the fundamental mystery. One intriguing consequence of the revised map concerns the concept of the galactic tide. Just as the Moon's gravity raises tides in Earth's oceans, the galaxy's gravity raises tides in the solar system. The galactic tidal force is incredibly weak compared to the Sun's gravity at planetary distances, but it becomes significant in the outermost reaches of the Oort cloud, where comets orbit at distances comparable to the spacing between nearby stars. At these distances, the galactic tide competes with the Sun's gravity, and perturbations from the tide can gradually alter cometary orbits over millions of years. The strength and direction of the galactic tide depend on the local mass distribution, both visible and dark. The revised distance and the updated models of dark matter density in our neighborhood change the calculated tidal force. Most estimates put the change at a few percent, which sounds trivial but matters when integrated over the age of the solar system. A slightly different tidal force means a slightly different rate of comet injection from the Oort cloud into the inner solar system. This affects impact rates on Earth and other planets, which in turn affects the long-term habitability of those worlds. The connection between galactic dynamics and biology might seem far-fetched, but the links are real and measurable. Cosmic ray flux influences atmospheric chemistry, which affects climate. Supernova rates influence the interstellar radiation environment, which determines mutation rates in surface-dwelling organisms. Stellar encounter frequencies influence comet impact rates, which drive mass extinction events. Each of these chains connects galactic-scale phenomena to planetary-scale consequences, and each depends on knowing where we are in the galaxy with precision. The infrared telescope's contribution extends beyond correcting old errors. It also opened new windows on galactic processes that previous instruments could not observe at all. One example is the study of embedded star formation, the process by which new stars ignite inside dense molecular clouds. These clouds are opaque to visible light, hiding the younger stars from optical telescopes. Only infrared and radio observations can penetrate the dust and reveal what happens inside these stellar nurseries. The infrared data showed that the Orion Arm contains far more active star-forming regions than optical surveys had detected. Many of these regions were completely unknown before the infrared observations. They appeared as blank patches of sky in visible light, seemingly empty stretches between known stars. In infrared, they blazed with the warm glow of newborn stars, still wrapped in their natal gas and dust. Some regions contained hundreds of protostars, stellar embryos still accumulating mass from their surrounding disks. Others contained young stellar clusters that had recently cleared away their birth clouds and were now flooding their environments with ultraviolet radiation. The discovery of these hidden star-forming regions has consequences for understanding our local environment. Massive stars formed in these regions produce copious ultraviolet radiation and eventual supernova explosions. Their influence extends thousands of light-years. A star-forming complex a few hundred light-years away that was unknown before the infrared survey might be producing massive stars right now that will explode in a few million years. If one of those explosions is close enough and oriented unfavorably relative to Earth, the consequences could be significant. This is not a cause for alarm in any immediate sense. Supernovae close enough to directly threaten Earth occur extremely rarely, perhaps once every few 100 million years. But the infrared data allows us to assess the risk more accurately by mapping the distribution and ages of massive stars in our neighborhood. We can now identify which stars will explode first, estimate their distances, and calculate the radiation dose Earth would receive. In most cases, the dose is negligible. The stars are too far away, or the intervening material attenuates the radiation too much to cause measurable harm. But in a few cases, the proximity and orientation are close enough to warrant monitoring. The study of star-forming regions also reveals how new planetary systems form in our galactic environment. The chemical composition of the gas and dust from which planets coalesce reflects the local enrichment history. How many generations of stars have lived and died in this region? What supernovae have occurred? What neutron star mergers have contributed rare heavy elements? The infrared spectra of molecular clouds in the Orion Arm show a rich chemical inventory: water ice, carbon monoxide, methanol, formaldehyde, and more complex organic molecules that serve as precursors to the chemistry of life. The clouds that will collapse to form new stars and planets in our neighborhood are well stocked with the raw materials that biology requires. This chemical richness is a consequence of our galactic position. We sit in a region that has been enriched by multiple generations of star formation over billions of years. Not as enriched as regions closer to the galactic center, where more stellar generations have contributed, but enriched enough to produce rocky planets with diverse compositions and complex surface chemistry. A solar system forming today from material in our neighborhood would have access to all the elements needed for Earth-like geology and Earth-like biology. The infrared telescope also contributed to understanding a phenomenon that connects our galactic position to the very largest scales in the universe. Our local group of galaxies, dominated by the Milky Way and the Andromeda Galaxy, moves through the cosmic microwave background at a velocity of about 600 kilometers per second. This motion is driven by gravitational attraction from large concentrations of mass at cosmological distances, including the Laniakea supercluster, of which our local group is a member. The telescope's precise measurements of stellar velocities in our neighborhood helped refine the decomposition of observed motions into galactic rotation, local streaming, and cosmological flow. This decomposition is essential for cosmological measurements that use galaxies as reference points. Any error in subtracting out the Milky Way's internal dynamics propagates into the measurement of the universe's expansion rate, which is currently one of the most contentious topics in all of physics. The revised galactic parameters did not resolve the Hubble tension, the discrepancy between expansion rate measurements made locally and those inferred from the cosmic microwave background, but they sharpened the tools used to make local measurements, reducing one source of systematic error. If the tension persists after all known systematics are accounted for, it will point toward new physics beyond our current models. The infrared telescope's contribution to this effort, while indirect, underscores how getting our own galactic address right has consequences that extend to the fundamental physics of the universe. Looking forward, the revised map raises questions that current observations cannot yet answer. How exactly does the Orion Arm connect to the broader spiral structure? Is it anchored to the galactic bar like the established major arms, or does it exist as an independent feature, perhaps a bridge between two other arms? The current data hints at both possibilities without definitively resolving the question. More observations at longer wavelengths, probing deeper into the dusty plane, are needed to trace the arm's innermost extent and determine where it originates. How does the spiral pattern evolve? The arms are density waves, not fixed structures, and they change shape over hundreds of millions of years. Will the Orion Arm grow or shrink? Will it merge with Perseus or Sagittarius as the galaxy evolves? Simulations can explore these possibilities, but they require accurate initial conditions that only come from observations like those the infrared telescope provides. What is our dark matter environment really like? The current measurements constrain the local dark matter density to within broad limits, but the nature of dark matter particles remains unknown. If dark matter is a single type of particle, the density profile follows certain predictions. If dark matter consists of multiple components or interacts with itself in ways we have not detected, the profile could differ. Future experiments, both astronomical and laboratory-based, will explore these possibilities. The infrared telescope's contribution is to provide the gravitational map against which these experiments can be compared. Where exactly did our solar system form? Our current position does not necessarily reflect our birthplace. Stars migrate through the galaxy over time, pushed by gravitational interactions with spiral arms, molecular clouds, and other stars. Some models suggest the Sun formed closer to the galactic center and migrated outward to its current orbit. Others propose formation at roughly our current radius. The revised galactic map constrains these migration scenarios by providing a more accurate framework for the dynamical models. Tracing our origin requires not just knowing where we are now, but understanding how the galactic potential has evolved over the past 4.5 billion years, a challenging computational problem that the new data makes more tractable. What threats lie ahead on our galactic journey? We know about the vertical oscillation through the plane, the radial oscillation inward and outward, the approaching Perseus density wave, the interarm void beyond Sagittarius, and the stellar streams threading through our neighborhood. But there are surely hazards we have not yet identified. The story of our revised galactic position is, in the end, a story about the relationship between knowledge and reality. For a century, we believed we knew where we were. Our measurements were consistent, our models were elegant, and our confidence was high. Then, an instrument capable of seeing what we could not see revealed that reality was different from our map. Not just a little different, profoundly different. Different enough to change the answers to fundamental questions about our safety, our history, and our future. The experience should make us humble about what we think we know today. The infrared telescope is extraordinary, but it is not the last word. Future instruments will probe wavelengths and sensitivities beyond its reach. They will find errors in the current map, just as the current map found errors in its predecessor. The process of discovery is not a march toward a final answer, but an endless refinement. Each generation's best measurements becoming the next generation's starting assumptions, which in turn become the errors that the generation after that discovers and corrects. This is not discouraging, it is liberating. It means there is always more to discover, always deeper truths to uncover, always a better map to draw. The galaxy we thought we knew was a story we told ourselves in the absence of better data. The galaxy the infrared telescope revealed is closer to reality, but still incomplete, still partially obscured, still full of surprises waiting behind the next veil of dust or hidden in the next wavelength of light we learn to detect. We live on a small rocky planet orbiting an ordinary star in what we now know is a major spiral arm of a barred spiral galaxy. We are 29,000 light-years from a supermassive black hole, moving at 500,000 miles per hour, bobbing up and down through a disk of gas and stars, wobbling inward and outward as gravitational forces push and pull us from every direction. Streams of stars from destroyed galaxies flow through our neighborhood. Dark matter we cannot see provides most of the gravitational force that shapes our orbit. Radiation from sources we are still cataloguing bombards us constantly. Ancient star clusters on intersecting orbits approach and recede on schedules measured in hundreds of millions of years. Ahead of us lies a void between spiral arms that we will cross in 50 million years, followed by a new arm with different conditions and different hazards. This is our cosmic reality. It is more complex, more dynamic, and more breathtaking than anything the old maps suggested. And it is the foundation on which the next generation of questions will be built. Where else does life exist in this galaxy? How common are the conditions we enjoy? What determines whether a planetary system in the galactic habitable zone actually develops complex biology? How will our environment change over the next billion years as the galaxy evolves, as spiral arms shift, as the Milky Way approaches its eventual collision and merger with Andromeda? These are questions the infrared telescope has sharpened, but not yet answered. They will occupy astronomers, astrobiologists, and planetary scientists for decades to come. Each answer will rest on the foundation of knowing where we are, truly, accurately, and without the systematic biases that misled us for so long. That foundation is now stronger than it has ever been. And from it, we can look outward with clearer eyes, humbled by past errors, guided by better data, and driven by the same curiosity that made our ancestors stare up at the pale river of stars arching across the night sky and wonder where they stood. The journey continues. The orbit continues. The galaxy turns, indifferent to our questions but generous with its clues. And somewhere in the infrared glow of a universe we are learning to see, the next correction waits to be discovered, the next comfortable certainty waits to be overturned, and the next version of our cosmic address waits to be written, closer to truth than the one before, but still not the last word.